One of my friends calls the mean value theorem the mean all value theorem, and I disagree. I think it's actually a pretty nice theorem, and it's incredibly useful. It's really one of the most useful things as far as how we can use calculus to make and analyze models, and that's what we use calculus for. So I've taken the liberty of doing a picture in advance, and there are a couple of things to be pointed out here. So I've got this curvy thing is the graph of some function y equals f of x, and I've labeled 2 points, a comma f of a, b comma f of b, and I've drawn the secant line. Remember, secant is Latin for cutting, that goes between those 2 points on the graph, and I've written its slope. Slope's a fraction. The bottom is b minus a. The top is f of b minus f of a, and so there is the secant. This is all very familiar from pre-calculus, I assume. Okay, so now we're going to throw something else into the mix, which is a tangent line. And it seems pretty intuitively clear to me that one of those tangent lines, like the one I've just drawn in purple, is parallel to the secant line that also represents the average rate of change. And so that's right. That's what happens. There is a tangent line that's parallel. So over the years, mathematicians have settled on a name for the point where this tangent line occurs. It's Greek. It's the Greek letter xi. And of course, the value of the function there is f of xi. You're going to see in a second that this doesn't matter. I mean, that's the name, xi. And if you like drawing squiggles, go for it. Anyway, what we see here is that f prime of xi, that's the slope of the tangent at this point that we don't know, is equal to that difference quotient that we're accustomed to as a fraction. The bottom is b minus a, and the top is f of b minus f of a. And so there is some point. There is such a point. You don't know what it is. You don't need to know what it is. You can use it very effectively without knowing what it is. If anyone tells you to find out what it is, you tell them to find something else to do to bug you because they're not being nice. The point is, you don't need to find this point. You just need to know there is one. And so that is the situation with the mean value theorem. That's the mean value theorem. Now, I have to admit, that doesn't sound very useful on its own. And so let me illustrate what's going to happen here. And what's the key is knowing the sign of the derivative, not the value, but the sign. Is the derivative positive? Is the derivative negative? That's all that matters. And so that simplifies also the calculations that sometimes you end up doing when you're working with these things, because all you care about is the sign. So you don't have to worry about squared factors. You don't have to worry about exponential factors. Those are always positive. Those can't change the sign. Constants, positive constants, can't change the sign. All that matters is the sign. All that matters is the sign. And so here's the situation. And we can see it if we go right back to this thing. B minus a is presumably positive. If not, f of b minus f of a changes sign as well. And so what you're seeing here is that f of b minus f of a and b minus a, their signs are related by the sign of this derivative. So if you know that derivative is positive, then you know that f of b minus f of a and b minus a have the same sign. Now, that means that f is an increasing function in that interval. So I'm going to write this in kind of a shorthand. It's written down very explicitly in other cases. If f prime is positive, that means that f is increasing. So let me put stars and spangles and knots and other fancy stuff, some fireworks and the like around this, because this is how we use the mean value theorem. We see the sign of the derivative, and that tells us about the behavior of the function. And there's a subtle point to this that needs to be emphasized, which is if you have a function, you take its derivative and find the sign, and the sign of the derivative tells you over an interval where it's constant, where the sign is constant, how the function behaves. Well, what if that function is the derivative of something else? Doesn't matter. Its derivative being positive would tell you that it is increasing. And if it happens to be the second derivative, well, its derivative, that's the third derivative. So you get this whole cascade of implications. If f double prime is positive, that means that f prime is increasing. That is actually quite a useful thing. If f triple prime is positive, I do occasionally work with third derivatives, so this isn't just egghead stuff, then f double prime is increasing. Whatever happens, you take off one derivative and you get increasing. So these are these other rules that you might see. F double prime tells you something about f prime. F triple prime tells you something about f double prime. F the seventh derivative tells you about the sixth derivative, and so forth and so on. But those are just applications of this to functions that have come into our lives through various methods that we may or may not like. But it still applies. Doesn't matter where the function comes from. This still applies. Okay. So one big application or illustration of this is something that you've studied before in pre-calculus. And so that's going to be kind of our big illustration about how to use this. It's concavity. And so I'm going to draw us a couple of curves. One is concave up and one is concave down. We're also going to talk about maximum and minimum, so I might as well point out maximum here, minimum there. Anyway, what is going on here? And let me show you something that is really crucial as far as thinking about calculus. And so I'm going to draw a couple of tangent lines on each of these curves. So now the derivative, it's wonderful. It's the slope of the tangent. It's the rate of change. It does all kinds of things for you. So in this case, what we have is the derivative starts off being negative and ends up being positive. So I'm just going to write that informally. F prime is negative, and then f prime is positive. Well, you know what? When you go from negative to positive, that's an increase. You don't need to know negative what to positive what. Something starts negative and ends up being positive, that's an increase. And so what you're seeing here is that f prime is increasing. It goes from negative to positive. That can only happen if f double prime is positive. And so the second derivative, the sign of the second derivative, not the value, the sign of the second derivative tells you that the concavity. In the opposite situation, we have that f prime goes from being positive to f prime being negative. This is so simple. If you go from being positive to negative, that's a decrease. So what we have here is that f prime, I didn't calculate it, I just looked at it and said, hey, look, there's a tangent line, there's its sign. There's another tangent line, there's its sign. Oh, the slope decreased, it went from positive to negative. So we have f prime decreasing. F prime is the slope of the tangent, and that only happens if f double prime is negative. Now, sometimes putting this into action involves some algebra, but remember, ignore squared terms. Ignore squared factors. You have to factor it correctly because squares don't change the sign. ignore exponentials because exponentials don't change the sign. And so what you'll see in a lot of situations is you have something where the algebra looks pretty complicated and you can ignore most of the terms and use that. So we'll illustrate that later, but that's the deal. So quick review. Mean value theorem, not in its useful, I'm sorry, that is its useful form. There's the not useful form. There's the useful form, some consequences, and some geometric illustrations of what the mean value theorem does to you. And remember, it's the sign, not the value. We don't value values. We only value signs. So there's something to have fun with.